Previously in CPLEX, we learned how to go about declaring decision variables when we are making linear programs. In that case, we do things like dvar float voltage. Okay, and that would create a decision variable called voltage that could take on real values, positive and negative. We could also do things like dvar float positive, maybe name our decision variable x1. And in this case, x1 had to be greater than or equal to 0. Lastly, we learned a couple other cases like using booleans. And actually, we need semicolons after we do this, right? We can also talk about integers. All right. So in each of these cases, these were decision variables. Now, CPLEX gives us the ability to define constant values. Now, it's actually going to end up being pretty similar, except we're going to leave off the dvar notation to indicate that it's a decision variable. So what does that look like? Well, we could say something like float my age is equal to 63.5. We could also do integers, like maybe we have something called slices of pi, and we could set slices of pi to equal 6. So in these cases, what we're doing is we're introducing a variable and assigning it a value. Now, typically these values don't really change. At least not in the sense of like a decision variable where we're trying to solve for them. We can also define variables to be a function of other variables. So let's say I define a float, and maybe I can define a new variable y and say that's equal to my age times slices of pi. Okay, you could certainly do that. Lastly, the last type of variable we're going to introduce is we can also use strings. Now, this is probably going to be a little bit less common, but it's certainly an option. So maybe we have a string called my name is. And we'll assign it using double quotes, Slim Shady. Okay, and of course, if we're actually doing this in CPLEX, we would have a semicolon afterwards. So let's actually do this really quickly. So I just opened up a blank mod file in CPLEX, and you can see I can do stuff like float my age is 65.3 and semicolon. Right, I can do int slices of pi equals 6. I can also say again x or y is equal to my age times slices of pi, semicolon. So these are all allowed, and again you can see we can also define a string. My name is Slim Shady. Okay, a few things to notice here. For the strings, we have to use double quotes. And actually, the last thing that I want to sort of point out is we can't define Booleans. So even though we can have a Boolean decision variable, we can't say Boolean stay or go equals true. Okay. You can see we're getting some sort of error. And the error here says, can use the type Boolean only for decision variables. And so it seems like Boolean is not a type of variable that we can use to assess something as true or false. But that's not to say there aren't other ways we might be able to define some sort of Boolean type variable. We could create a variable called stay or go, and we could set it equal to 0 to indicate staying, or we could set it equal to 1 to indicate going. Later on, we'll learn how we can use logical if statements or control loops within CPLEX where having access to Boolean values might actually be useful. All right, so let's actually see where this comes into play when we're doing a program. All right, so I'm going to delete this all, and I'm going to write a linear program where we're going to use these constant values to sort of update a problem. All right, and so let me give you an example. So let's say I was trying to figure out how many cats I should get. All right, and the number of cats that I'm going to get is based on how much food I can afford to buy each week. So I'm going to define this variable called max food. And I'm also going to define the number of cats that maybe my landlord allows me to have. So in this place, it's 5. Now I can then introduce a number of decision variables. So I'm going to make these all integers, and they're going to correspond to the number of different types of cats that I might want, right? So I might have a number of black cats that I can get. Oops, actually. Why devar, sorry, that's why. And I'm going to say it has to be a positive integer. We can talk about the number, let's say, street cats that I take care of, and maybe the number of mean cats. Right. So at this stage, I can start writing an optimization. So let's say I want to maximize my happiness. Is that how you spell happiness, or is it with an I? All right, so my goal is to maximize my happiness subject to some constraints. All right, so my first constraint, I might as well go define what happiness is. Right? So in this case, happiness is going to end up becoming a decision variable, and so I'm going to make it a float. So maybe happiness is equal to 5 times the number of black cats that I have, plus 2 times the number of street cats, plus 1 times the number of mean cats. And I actually spelled. Okay. Right, semicolon. And let's say, well, we'll just leave it at that. Okay. So now we're going to start introducing some constraints. I need a double equals. Right. So we always have double equals for our constraint equations. Now let's take into account constraints related to maybe the amount of food that I have or the maximum number of cats. So we can certainly imagine that if my total number of cats has to be less than or equal to 5, I can say the number of black cats plus the number of street cats plus the number of mean cats has to be less than or equal to max cats. Okay. The next constraint might relate to the amount of food, right? So maybe black cats tend to eat, 3 pounds of food a week. My street cats, they eat some food outside in the street and some food at home. So they only need, 2 pounds of food a week. But my mean cats, maybe they eat a lot of food. So they take up 4 pounds of food a week. And all this has to be less than max food. Okay. So now that we have this optimization program, I can go ahead and run it. Oops, why is it saying I have some variable x? I'm not sure. Oh, that's all. Okay. And here you can see my happiness is 15 units, which is great. I end up with 3 black cats. So I actually don't get all 5 cats that I'm allowed to. Let's say I get a raise, all right? And I can now afford more cat food. I can easily rerun this program just by changing this value from 10.5 to maybe now I can afford 20 pounds of food per week. And so now I can easily rerun this program just by changing that value. And all of a sudden I get 5 black cats. So I am very, very happy with that. So that's good. Actually, let's try changing it to 21. Maybe I can get another cat. Can I get a mean cat? No, we'll do 22. I think I might be able to get a street cat. Let's see. Oh, no street cats. I'm going to ask my landlord for 1 more cat. So he decided to let me have 6 cats. Oh, and I keep getting black cats. Wow. I really like black cats. I'm surprised. So it might be worth figuring out which one of these constraints is active. 6 cats. How much food do I get? Oh, yeah. So the constraint isn't the food. It's the number of cats. All right? Let's say my landlord went nuts and said I could get 15 cats. Let's find out what happens. Ooh. So the constraint seems to be the food here. I would think that I'd be able to get at least 1 street cat. So maybe I need to make this 23. Because here I'm getting 7 black cats. Times 3 would give me 21. So I think I need 2 more pounds of food so I can get a street cat. So this is good. Oh, there we go. I got a street cat. All right, so now I'm even happier. 37 units of happy. Anyways, so this is sort of a fun way, or not really fun, a useful way that we can redefine variables that make up the constraints. And certainly we could even talk about how much food a street cat eats. So maybe it ends up that street cats don't actually need 2 pounds. Maybe they only need 1 pound of food. Okay? And so I can actually change that and put it into the coefficient here, right? Oops, and I forgot a semicolon. So let's try that again. I think it's going to spit back an error. Yeah, oh, spit back an error because I was missing the semicolon. And there we go. So now, if my street cats only take 1 pound of food a week, right, I can resolve this optimization, and now it looks like I get 11 street cats. And I hit my max cat quotient of 15. So anyways, this is sort of a neat way that we can not only change the right-hand side of the constraints, but we can actually change the coefficients in the constraint equations. Likewise, we could also do that in our cost equation, right? So there's not really a limitation here. So maybe I want to scale happy by 2, okay, for some reason. So we could certainly take happiness and multiply it times scale happy. And this is perfectly acceptable. So maybe I underestimated how happy I get from having cats. And the reality is I'm actually twice as happy. And so now you can see when it solves the problem, we end up with 42 is happiness, but the objective function ends up being 84, which is twice as much. So this is sort of a useful way in which we can use constant variables, or just variables in general, as part of CPLEX that are not necessarily decision variables.